Welcome to Chapter 9 of Physics with Calculus for Aquinas University. We'll be going over linear momentum and collisions today. As with everything else, this is an expansion on previous topics. The equations at this point can get pretty complicated in their actual work, but they come from simple concepts, relatively speaking. So keep in mind as we're going through the examples that we go through that if you write down your initial preconditions and your initial variables and your knowns, your unknowns, and then just follow the steps, follow the equations that make sense, you're going to find this stuff to be very doable. You just got to take your time and write it down. As always, I'll be going back and forth between the OpenStax created slideshow and the textbook that's available on OpenStax for you to read. This is not meant to be your only source of this information. Please look elsewhere. And with all that said, let's begin talking about linear momentum and collisions. So what are we talking about here? Well, this chapter goes over impulse, momentum, and center of mass. Those are three interconnected ideas and really interconnected mathematical equations that describe interaction between objects, essentially. Momentum is at its most basic level, your mass times your velocity. Impulse is how long you apply a force to change momentum, and center of mass is kind of the way things actually work in this physics sense. And there's all this math behind it. We'll get into that, but at a very base level, that's the equations, right? Mass times velocity is momentum. Force times time is impulse, and center of mass is a calculated parameter of anything you talk about. So, as said before, mass times velocity describes momentum. It describes the way things work and why they work the way they work. For example, soccer or football, if you prefer, works because the ball is light, right? And if it was a bowling ball, you won't be able to move it as fast. Why? Because the bowling ball is heavier, right? That's an obvious thing to anyone. It takes more effort to move something heavier. And it takes more effort to stop things that are heavy, that are moving. So a soccer ball or football does a very good job of directly translating the velocity given to it into the velocity outputted by the ball, right? The harder you kick the ball, the faster it goes. The softer, the more delicate you are, you can dribble the ball and not lose it, right? You can't do those things with heavier balls or lighter balls necessarily, right? Anyone that's ever tried to play wiffle ball knows you really can't throw a wiffle ball too well. Of course, this also applies to large objects. The super tanker that was caught in the, I think, Suez Canal a couple of years ago took a lot of effort to dislodge because heavier things take a lot more effort to move. If you really increase your mass, you have a small velocity to compensate and vice versa. So in a very non-mathematical approach, that's the concept, at least of momentum. This goes down to the micro scale as well, of course. Gas and gas pressure. Pressure is the force gas imparts on the container, right? Gas molecules more or less freely bounce around willingly however they want. And we describe the changes in velocity when they bounce off something as instantaneous. And well, it's not technically instantaneous. Obviously, that's an impossibility. That is practically instantaneous because the masses of particles are so small, changes in momentum, that velocity, right? Remember, velocity is a vector, right? Changes in that momentum due to changes in that velocity can happen with little force needed. Gas pressure comes from the amount of particles, not the particles themselves. Again, another example of this concept. This is the impulse example. So I said momentum is mass times velocity. Cool. big mass, low velocity, low mass, big velocity. Impulse is the amount of, is how long you apply a force to something. And impulse is directly related to momentum because, as this image shows here, the longer you spend applying the force, the more momentum the thing has. Because force is directly related to acceleration, right? So the larger, but you don't have to necessarily change the force, you can just change its amount. This goes into the pressure area conversations that we had before. In this example here, part of the reason that a soccer ball or football is not solid is it allows the foot to impress into it and keep applying the force throughout. Anyone who's ever played baseball or golf knows you're supposed to follow through in your swing. You follow through in your swing because the more you follow through in soccer too, or football, you follow through with your kick. The more you follow through, the more time you're impacting a force onto an object, and thereby increasing the momentum the object has. Here, T naught being time, the topic's football there has a T naught and then a delta P. The bottom football has a 2 T naught and a 2 delta P. They are directly related to one another. The longer you apply the force, the more force is applied. Right? So again, the same sort of concept with area and pressure. Sports is a common analogy for this because it's true. You will not, if you take like a very solid object, like, you know, a chunk of wood or something, and try to play tennis, you're not going to do as well because the give a tennis racket has directly relates to not only the control of the ball, but also the speed of the ball when it leaves the racket. And tennis rackets, there's an entire industry there for a reason, because tennis rackets have different strengths, and those strengths can play in different ways with the ball. So that all being said, let's go to our first example, 9.1, dealing with the very famous Arizona meteor crater in Flagstaff, Arizona. I did skip over some of these equations in my initial high-level conversation, but here they are, and here's what they look like. Your impulse is directly related to your force and your time, so your F sub t and your delta t, dt there. And of course, those things coming down here, average force, again, directly related to time. So approximately 50,000 years ago, a large, radius 25 meter, nickel iron meteorite collided with Earth at an estimated speed of 1.28 times 10 to the fourth meters per second. Pretty fast. And it was now northern Arizona desert in the United States. The impact produced a crater that's still visible today, right? That's obviously very visible. It is approximately 1,200 meters, or 3/4 of a mile in diameter, about 170 meters deep, and has a rim that rises 45 meters above the surrounding desert plain. Iron nickel meteorites typically have a density of 7,970 kilograms per cubic meter. They're heavy. Use impulse considerations to estimate the average force and maximum force of the meteor applied on the Earth during its impact. Cool. So what does this ask us to do? Well, it's conceptually easier, you could argue, to reverse the question and calculate the force the Earth applied on the meteor in order to stop it. Because the meteor obviously had some initial velocity, a given, right here, and it had an obvious final velocity of 0. And it's a lot easier in math if you can hold something still. Because if you set things to zeros, you delete parts of equations, which is super, super useful if you can do that. If we want to consider the Earth, of course, was moving in various frames of reference when this asteroid hit. But if you don't worry about those things, you can solve the direct problem. You don't want to care about how fast the Earth was moving around the sun and the angle. You don't want to worry about all that stuff. That's asking way too much for the question. So the book, and I would suggest, let's consider the force the Earth applied to the meteor in order to stop it. It's Newton's third law. So we can calculate the force on the meteor and then use Newton's third law, there you go, to argue the force from the meteor on the Earth is equal to magnitude in opposite direction, right? Using the given data about the meteor, and making reasonable guesstimations about the shape of the meteor impact time, right, for sake of conversation, you can calculate the impulse, and then you can use the relationship between force and impulse. Again, what we said earlier, impulse is equal to force times time, or delta t. Estimate the average force during said impact. Average force, again, given right here, 9.5. Next, you can choose a reasonable force function for the impact event, calculate the average velocity from 9.4, right here. Sorry, right here. Right, integrate over said time change, and set the resulting expression equal to calculate average force. If you know average force, you can solve maximum force. Cool. So define our vectors, define our coordinates here. We're going to say, for sake of conversation, that upwards is the positive y direction. It's kind of obvious, right? And we assume, let's just assume from the question that the meteor is traveling essentially vertically prior to impact. In that case, its initial velocity is negative vi j hat, right? Because it's moving in the negative y direction. The force that exerts on it, by definition, would be some force in positive in j hat. Situation depicted in the picture, of course, would be time equals 0. That's when the meteor strikes the Earth. So from it moving, as soon as it touches the Earth, start your clock, and when it stops moving, when velocity is 0, end your clock. So average force, of course, given by equation 9.6 as shown above, is equal to your impulse, your j vector, over your change in time. And we know that j vector, your impulse, is also related to the mass times the change in velocity, because change in velocity dictates, again, your change in velocity was given, as said before, up here, and that relates to the momentum, as we talked about before, because momentum is your mass times your velocity. If you change the velocity, therefore you change the momentum. If you're impacting a force onto something, you're changing its velocity. Obviously, this meteor's velocity is changing, it's going to 0. And this allows us now to use delta V in the equation. Delta V was something that we're given. So part of building these equations, if you don't know what to do, is look at your variables, look at what you know, look what you don't know, see if there's an equation that can relate them, right? We were doing that stuff way back in like chapter 2 and chapter 3. This is just a more complicated version because you got so many equations to deal with. Mass, of course, is given by density and volume. So we can guesstimate a roughly spherical meteor, for sake of conversation, meaning the volume is 4/3 pi r cubed, to obtain a big looking equation for the average force by substituting in m for the mass and for the density and the volume and stuff like that, giving us an equation for average force. So now we can plug and chug in things that we know. We know the initial velocity, right? We know vi, and we can guess 2 seconds of impact. We're guessing that because that seems reasonable. We weren't told that, but we need a delta t, so let's go ahead and use a delta t of 2 seconds. If we do that, we find that this meteor going at that speed, taking 2 seconds to stop, would give us a average force of the Earth impacting on this meteor of 3.33 times 10 to the 12th newtons. All right. This is the average force applied during a 2-second stoppage, essentially. We're negating force of the meteor, exploding and stuff like that. We're negating all those. We're only focusing on the thing we care about, like the meteor kept its consistency, right? Force points in the same direction as the change in velocity for delta V. So in order to calculate maximum force, we can then integrate f of t dt over that impulse from ti to t maximum. It's of course important to make a reasonable choice for the force as a function of time. So we can define t0 at the moment the impact happens, and then we assume the force is a maximum at impact and rapidly drops. Why do we assume that? Because that's how it works. right? So we can arrange our equation based on that assumption, where delta t, of course, is our t maximum, or the amount of time it takes to do this, minus 0, because 0 is where we started. Since we already have a numerical value for the forced average, which was given up here at the top, given our 2-second guesstimation of impact time, we can use that result, therefore, to create a t maximum. And, well, plug and chug in our numbers here, as we've been talking about before, and we land at a force average is equal to slightly under half of the force maximum. Thus, our force maximum, flip it around, we get 7.27 times 10 to the 12th newtons. Again, cool, useful. I like it. We are taking complicated questions, not given enough information, and deriving out what we need to solve the problem. Why did we have to guesstimate a time? Because our equation ended up having time in it, so we need to fill that variable, right? This is very applicable to a lot of higher end mathematics. You're not always going to be given all the parts you need to solve a problem. You have to figure out where this comes from and how this works together in order to solve them. Cool. That was the media question. Impulse, of course, is very variable in a lot of engineering applications. Your airbag saves your life because it increases the impulse of your face stopping. Your face stops very fast on your dashboard, and it stops a lot slower in a bag of air. Slow enough that instead of your face exploding, you maybe break your nose. And you're happy about that because you don't want your face to, explode on the dashboard. The book does go in pretty good detail with lots of examples going over various aspects of what we just did. I do very much suggest that you take the time, if you're not understanding this concept, and go through those individual examples I did not go through. This is a math equation. This has a math component to it in the book. Feel free to take your time and do it. I alluded to this earlier, but impulse and momentum are directly related to each other. When you apply an impulse, you're applying a force over a set amount of time. The more force you apply, the more you're changing the acceleration, F equals ma, and therefore the more you're changing the momentum, because acceleration is changing velocity, right? So your momentum is directly related to the change. Your impulse is your change in momentum. If you change some variable, and it's usually the velocity of something, you all have to apply a force, and that force therefore takes some amount of time. Right? These are all, again, arguably straightforward concepts, things you do every single day in life, but now you're kind of learning the mathematics behind the conversation. This illustration here, expanded more greatly in the book, right here, kind of goes over this base concept. Essentially, when you kick a soccer ball or a football, shown here, you give an amount of force over an amount of time to the object, and that a force and time you can then describe as vectors, and then you can just vector addition them to see what happens, right? In this case, you have an impulse at an angle, and then you have a momentum being carried by the velocity. And since the impulse is additive to the momentum, you're changing it, you therefore have an increased velocity and possibly a change in direction of that velocity, since it's a vector, due to that impulse. And this is actually going to play a bit in a couple more sections here. We go into multiple dimensions, because it's important to remember that all this stuff ties back to what we did in chapter 3 and chapter 4. We're keeping your dimensions set. Your I hat, J hat, K hat, your X components, Y components, Z components, stuff like that. All of that is coming up again. Cool. Funny enough, Star Trek calls their rockets impulse engines, because the technology is distant future sort of stuff. Again, the book goes over examples that are of interest. I highly suggest you do them if you're getting lost in this chapter. I chose 9.4 to go over instead, which is dropping an iPhone. We all drop our phones all the time, right? Let's go over some math behind that. Apple released its iPhone 6 Plus in November 2014. According to many reports, it was originally supposed to have a screen made of sapphire, but that was changed last minute to a hardened glass screen, which is what we all kind of have nowadays on our phones. Reportedly, this was because the sapphire screen cracked when the phone dropped. What force did the iPhone 6 Plus experience as a result of being dropped? So, what was this force that the sapphire couldn't handle? So, the force the phone experiences due to the impulse applied to it when the floor and the phone collide with each other. Essentially, the velocity going from some number to zero. And the amount of time it takes for that to happen is your impulse. We're going to use this idea of the impulse and the momentum there. We're going to change the momentum from some number to zero because mass times velocity is zero, momentum is zero. And then calculate the impulse, estimate impact time, and use this to calculate the force. So we're going to kind of use these equations backwards, right? We need to make a couple of reasonable estimates, as well as get some technical data from the phone, of course. First, let's suppose that the phone is most often dropped from chest height, right? You're using your phone, you drop it there from an average person's chest. Second, let's assume that it is dropped from rest. That is, you're not throwing your phone on the floor. And finally, let's assume the phone bounces a little because it's reality, right? So the height of its bounce is assumed to be negligible. It's not a bouncy ball, right? It does bounce. That's reality. But the fact that it bounces is not going to impact the question. It's going to crack in the first jump, not the second one. So, of course, you want to make sure that your coordinates are correct for this conversation. So we're going to find upwards in the positive y direction. We're going to give it a height of 1.5 meters, chest height, sure. And then, of course, it's going to start with a VI of 0, I hat. So the average force in the phone related to the impulse applied follows the equation F average equals impulse over delta T. And our impulse is directly related to our change in momentum. So our force is directly related to our change in momentum over the change in time. We know change in momentum is directly related to the mass times the change in velocity. So we can therefore discuss the different changes in velocity that would go when you drop the phone. You start with 0. At some point, the millisecond before the phone hits the floor, it's at some max velocity, which you need to calculate, right? Just free fall. And then when the phone hits the floor, you have some equal and opposite force that the floor applies to the phone, which is then the cracking force, right? So given these definitions, and again, drawing this stuff out helps a lot, right? Drawing out you don't need to draw an iPhone with a bunch of apps on it, but drawing this stuff out in your homework is going to help you solve your homework. With these definitions, change in momentum of the phone can be defined by the mass, of course, times the change in velocities. Your change in momentum is equal to your mass minus your velocities in question. Velocity I only relevant in order to discover velocity 1. Since we assume the phone does not bounce when it hits the floor, velocity 2 as well as 0. So our change in momentum is equal to the mass times essentially velocity 1, although momentum comes from the free fall. We can get the speed of the phone just before it's the floor using kinematics or conservation of energy, whichever you prefer. The book's going to show you conservation of energy because kinetic and potential energies going on here, right? When the phone is being held, it's max potential. When the phone hits the floor, it's max kinetic. Solve it out. Because V1 is a vector of magnitude, it is positive. So we take our velocity equation here. We only care about the positive side of things, rather than negative velocity, because we're dealing with reality. So we can insert this equation, mass times square root of 2g height, into our initial, where is it at again? Into this guy up here. to help solve for that change in momentum. So we can look at this equation now. Do we have everything we need to solve the problem? Well, I'm asking for the force impacted by the dropping of the cell phone. And I know my force is directly related to my change in momentum divided by the change in time, or my impulse, essentially. And I've reconstructed the equation to account for all of those variables. Namely, my momentum is in fact dictated by the energy of the drop. So my force is equal to m divided by m times the square root of 2gh over delta t. Finally, of course, we need to estimate collision time. They do that by kind of calculating how long it takes the object to fall its own height. You can just make up a small number here, and of course it would have worked. And you come to find out that there's about 36 newtons of force applied to the phone when you drop it from your height. So since an iPhone itself only weighs 1.68 newtons, when you drop your phone, the phone is experiencing 20 plus times its own weight in force. That's a lot, in case you're wondering. And that's using momentum. We're giving you the cool thing about this question is it's a lot of jostling of equations for a rather simplistic looking solution. I skipped over, which one was it? I skip over a equation later that is a complicated solution revolving on jostling equations. But these sort of questions, again, are most easily answered by you taking the time, going back to your notes and looking at what's available to you, and also knowing your knowns and knowing your unknowns. I'm not giving any information about momentum for momentum's sake, but I am giving information about velocities and heights, and these things are all interrelated to each other. Yep. So, as said before, this exact conversation goes over the variety of ways that things touch each other or impact each other in some way. Um, those were all in one direction, the Y direction. When you care about the other directions, you care about your different dimensions, X, Y, and Z. You just need to make sure to separate things out and then solve them individually, then recombine them again and draw lots of triangles. We've been drawing lots of triangles by this class. It's continuing. Of course, system of interest is vitally important, as we discussed earlier with the Earth meteor example. You need to care about what you need to care about, and you need to ignore what you need to ignore. And determining that at the very start of the problem is going to help you find a quicker solution. I skip over this, but again, if you're going through this stuff and you're like, I don't get it, this collision car example from the text is very good. Let me just scan up to the next chapter here. There we go. Cool. I guess I will say regarding these particular questions, linear momentum and conservation of momentum is a key connecting piece for a lot of these sort of problems, especially when we get into collisions. Conservation momentum essentially is everything you start with is what you end with, right? Matter energy cannot be created or destroyed, neither transformed. So everything that every amount of energy, the force and momentum interred in that quantity carry on throughout anything that happens. So that's what's going on here. Newton's third law dictates that you always have equal but opposite reactions. You need to account for everything. Of course, in real world, energy is lost in more ways than just momentum, light, sound, heat, stuff like that. But you can still care about those non-conservative forces and find your answers to be accurate. Question about Super Bowls dropping, classic hockey puck question. I chose the space one because I like space, but these four are all different questions in the text. If you're having issues, please go back through the text and read and try to understand these questions. They're all classics of physics, essentially. All right, so let's go to example 9.9. There we go. On November 12th, 2014, European Space Agency successfully landed a probe called, I want to say it was successfully landed a probe. I'm not going to say it, on Comet 67P. Big names that following that. This was super cool. I remember watching this live. During the landing, of course, the probe actually landed 3 times because it bounced along the surface. Calculate how much the comet's speed changed as out of just the initial bounce. When you'll see why they made it bounce around on the comet in order to land safely. So we're going to solve that problem given this stack of knowns here: mass of the comet, acceleration due to the comet's gravity, mass of the probe, touchdown speed, initial upwards velocity from the first bounce, and impact speed. Excellent. They give you a stack of information. They simply want to know the comet's change in speed. And why the comets? Because it is a comet did change speed. Every time you impart a force, you are changing momentum every single time. But momentum is mass times velocity, so you need a lot of force to affect a lot of mass. So we asked how much the comet speed changed, but we don't know much about the comet beyond its mass and acceleration and the acceleration its gravity causes. However, we are told that the lander collides with the comet and bounces off of it. This collision suggests momentum as a strategy for solving the problem. Why momentum? Because momentum is in parts a change in velocity. So if you know the momentum put onto something, and you remember that momentum is conserved, if you know how much the momentum of the satellite changed, or the probe changed, that's how much momentum also went into the comet. They're equal but opposite. You don't lose those things in any tangible sense. It's unless you have things exploding or catching fire or something ridiculous like that. The physical components of these things are preserved. We define the system that consists of the lander and the comet so that there are no external forces on the system. Of course, in reality, there are, but we're going to ignore those for this question. So we can, again, therefore say the momentum of the system is conserved. And then if we calculate change, as I just said, if we calculate the change in momentum of the lander, we know, therefore, the change in momentum of the comet, and we can backdate that to figure out the velocity change, or the force and therefore velocity. So the momentum of the first object, let's say the lander, is given by its mass times its velocity. We know its velocity right before it hit because we were told its touchdown speed 1 meter per second. Or in this case, negative 1 meter per second because it's going in the down y-axis. And we know its velocity afterwards as it bounced up. We're given those things. So we can determine its change in momentum by simply subtracting the two, right? That's what change is. That's what delta is. Notice, however, that when we subtract them, we do not have a negative sign. The change in momentum is positive 133. This is because it bounced back up, right? It was a lot of momentum was imparted back up due to essentially the big mass change of the comet, right? The comet's a lot larger. So we could then take we know that the change in the comet is the same momentum change as the change in the lander, equal and opposite forces, conservation of momentum here. And they're in opposite directions. The comet went up, so technically the asteroid, or the lander went up, technically the comet went down. But since change in velocity, change in momentum, and mass are all related to each other, we can figure out by a simple calculation as shown here that the change in velocity was 10 to the 11th scale. Practically indecipherable, thousandth of a billionth of a meter per second, right? The comet basically didn't change any momentum, didn't lose any velocity when the lander bounced off its face. But there is something there. It did change. The important part is that it's not zero. Since it's not zero, conservation of linear momentum was preserved. And that's kind of cool that we're nudging these things around. As a recording, 11/2/22, month or two ago, we like collided a very large lander rocket. We like shot a rocket into an asteroid and actually changed its trajectory on purpose because the asteroid, I think, was smaller than this comet, and we shot it with a lot more force, right? This lander wanted to land and take pictures, so it slowed down. If you want to move things, you need to have more force, you need to have more impulse, you need to have more momentum. Excellent. Again, the book goes over multiple examples of these conversations because the equations can get kind of daunting. I'm going to go over example 9.11 here, but when you're going through this stuff, if you just take good notes and slow down and write your stuff down, you're going to find that's really not too bad. 9.4 is types of collisions. These are elastic and non-elastic, and explosions are a type of non-elastic but backwards equation. Inelastic, there we go, not non-elastic, inelastic. The differences between these relate to that conservation of linear momentum, and they relate to what happens after the fact. An elastic collision is you start with two objects, you end with two different objects. A inelastic collision, you start with two objects, you end with one object, think like a car crash. An explosion is you start with one object, you end with two objects. But every one of those steps, you have a set amount of momentum or a set amount of energy in each individual part, and everything at the initial and everything at the final still need to equal out. So when you're dealing with any of these equations, if you can determine the momentum of the individual parts, you can determine the momentum at the end because everything needs to equal out. And that's what we're going to do. We're going to do an elastic collision here with hockey pucks. Two hockey pucks of different masses on a hockey rink. The red puck has a mass of 15 grams and is motionless. The blue puck has a mass of 12 grams and is moving at 2.5 meters per second to the left. They collide. It's perfectly elastic. Okay. So again, we're just doing, math magic here to have perfect elasticity of this collision. Given all those knowns, what are the velocities of the two different pucks at the end? So, as I said before, if we determine initial and finals, and we choose our chapter of the physics textbook to care, in this case, we're going to choose momentum. If we can know our initial or final momentums, we can then determine velocities from those momentums, given that momentum has to be conserved. The initial momentum is only in the moving object because a velocity of 0 means the momentum of 0, and the final ones each have a velocity. So our initial velocity is just m2v2i, and our initial momentum is that, and our final momentum is the first puck's m1v1 and the second puck's m2v2. We can also conserve kinetic energy again in the same manner. And in fact, we can merge these equations together to try to solve what we need to solve. Said before, there are two equations and two unknowns here. And the equations are pretty similar, right? But since we don't know V1 or V2, we can use substitution rules. Hopefully you remember that from algebra, to suss out the connections between them. The book skips the substitution rule. Just, you got to write a lot of stuff down. But when you do, you in fact solve out to find out that the big puck is moving in the positive direction, and the small puck actually bounces off and goes backwards. So again, write stuff down, take your time, work yourself through it. If you substitution algebra is all about just plug and chug and write it down. But when you do that, you do solve the problem. All of these conversations are are bigger than just like hockey pucks and footballs, right? The ideas of momentum plays a part in all factors of science. Rutherford's very famous experiments to determine that the nucleus existed in part came from um, studies of the momentum of the particles that he was shooting. So, like, we know neutrons exist, and kind of the idea of them being the majority of the mass of the atom from momentum changes given interactions. And that's pretty cool. When you do this again in multiple dimensions, if we go around like corners and stuff like that and circles, there's some examples in here in the text about that. You just got to remember your triangles and remember to break things down. Here we have collisions and XY component. I'll get to example here in a little bit. I chose a big example for this one, but if you see things in X's and Y's, keep your X's and Y's together, right? That's the whole point of this conversation here. And that's what's being shown here, right? This should look very familiar from chapters 3 and 4. Break down your components, solve, recombine your components. Cool. That all being said, let's explode a scuba tank and see what happens. Example 9.15. Of course, again, if you don't get it when I'm done, and I don't expect you to, please go back through the text and solve some of the other questions to elucidate a better understanding of the topic. So, example 9.15. Common scuba tank is aluminum cylinder that weighs about 31.7 pounds empty. When full of compressed air, the internal pressure tends to be between 2,500 and 3,000 psi. Suppose such a tank, which has been sitting motionless, suddenly explodes into 3 separate pieces. One of the pieces ends up being about 10 pounds and shoots off horizontally at 235 miles per hour. Well, I got a mass and I got a velocity, right? Therefore, I have a momentum. A second piece, 7 pounds, shoots off at 172 miles per hour on the horizontal plane, but at 19-degree angle from the first piece, so shoots off in a different direction. Can you find the mass initial velocity of the third piece? What happens to that third piece given these first 2 pieces? So all of that sounds like I have an initial momentum. So I have an initial set of conditions, and then I have a final blocks of momentum I need to solve for my third momentum, given all these things are related to each other. Or conservation momentum, let's close up our system, figure out our variables, and solve. We're going to define the system to be the scuba tank, and that makes this not a closed system, funny enough, since gravity is an external force. However, the problem asks just for the initial velocity of the third piece, so do I care about gravity for this conversation? Well, not really. Gravity is not like affecting the explosion in any significant way, right? So we can still consider the system to be essentially closed, because I need to remember that even though gravity is a part of this, gravity is not having a tangible effect on the equation and on the system. We also can have that initial problem of the momentum vector being 0 at the start. So let's choose our coordinate system, have all this stuff go down, write down our equations, and then solve for the third piece based on what happens in this coordinate system. So here's a big, actually, I think the book example is big. Good. So let's convert everything to SI units, of course, before we get going. Miles per hour into meters per second, pounds into kilograms, etc., etc. So, of course, we also are able to solve the mass of the third object, because we know the mass of the first and second object, and we know the mass of the entire system. So that's where that M3 comes from. It's 14, or the total, the actual thing. You get it. I'm not going to go in detail there. Let's sketch out basically what's happening and then determine what's going forward there. P1 is along the horizontal. P2 is along the horizontal, but like at a different angle. So this is sort of a top-down look. We're like hovering above, essentially. And then P3 is in some direction we're going to assume opposite of the first two because that's how explosions work, I guess. So sum up our x directional components. P1 and P2 and P3 all add together, would all add together to be 0. Yeah. Since we have conservation of momentum with all these equations, you can't break the laws of physics here. All the total momentum needs to equal 0 of the system. But each individual component is going to have its own momentum. They all just need to sum together. So in this case, P3 is equal to in the x direction, the momentum in the x direction is going to be equal and opposite the momentum in the x direction of objects 1 and 2. Right? That's what's saying here for top one, and that's the y direction is the exact same conversation. If I can figure out the momentum of the first and second pieces, the third piece would be equal but opposite to those in order for everything to equal 0 at the end. So we can solve out for x direction, y direction momentums by solving the individual pieces, right? Keeping in mind cosine and sine given this angle here. And then that susses out a magnitude, that susses out a momentum of our third piece there, which would be just Pythagorean theorem out, square root of the squares to determine our magnitude of our third piece, or the the magnitude of the momentum of that third piece. And then once we know the momentum, we can again extract out the velocity and the angle of that third explosion piece given the relationship between momentum and velocity. Breaking it down into its subsequent parts, remembering our x's and our y's, all crucial to this conversation. Last thing we're going to dive into is center of mass. Seems like a weird concept to be talking about this late, but it's actually kind of crucial to what allows all of these things to happen. Center of mass is super intriguing. This is like one of the first uses of photography for science was how the heck do cats always land on their feet? Well, they land on their feet by doing amazing contortion throughout dropping them. And that amazing contortion it's amazing because like a cat doesn't have the ability to like force things to make it move. So it has to use internal forces in order to reposition itself. And as we'll talk about here in a little bit, internal forces don't allow for external forces. So that's why cat landing on their feet is so interesting. What is center of mass? Center of mass essentially is the I just go to the book and read it that way. That'd be make my life a lot easier, right? There we go. Center of mass is the summation of all of the different momentums of everything involved in an object. Everything that's happening in an object, what that all comes together as is that center of mass. So when you treat an object, you don't necessarily need to care about the geometry of the object for a lot of these physics calculations. You treat the object as a dot. When we talked about the scuba tank exploding earlier, I didn't ask you to determine the geometry of the pieces flying out because the piece was one object. So we treated essentially each exploding piece of the scuba tank as a infinitesimally small point moving on a graph. And the results of that infinitesimally small point moving on a graph also correctly calculates the explosion to a very high percentage, right? Of course, that the metal warping and stuff would alter it a little bit, but these things are accurate, right? We don't need to care necessarily about the size of the billiard ball when we're calculating our pool because we calculate from center of mass. So let me get back down here. The book did a real good example of what center of mass is. I'm just trying to find the sentence that it said. I forgot it right here. Here we go. I think that's what I was looking for here. So above here is a whole lot of equations going over parts of an object and the forces inherent to them. And we're just kind of recombining and caring about momentum and stuff like that as we're going through, and force. We're relating force to momentum, and we're summing that over a set number of particles all moving internally. And all that stuff ends up with this guy here. So if we look at 9.28, we see a pretty complicated looking summation given some acceleration vector. And we notice that inside the parentheses, we're calculating the product of the particle's masses with respect to position. The J's there are actually every individual particle involved in whatever you're talking about. And all these particles moving around and given some vector and some mass, these all add up to an amount of particles, and then dividing the sum by the total mass of the particles is what we're doing inside those parentheses. All of this is reminiscent of an average and is inspired by, loosely interpreted, weighted average position of what we're talking about here. So everything, center of mass, as I said before, just to repeat myself here, is the dot that we use to represent an object, because the outside parts of the object all kind of surmise or sum to the same thing. Like, you don't need to care about the extraneous sections if I'm not asking you a question about the extraneous sections. This slide, or to expand it out a bit, this graphic here, I think also does a pretty good job of this concept. So let's give ourselves 3 different particles, M1, M2, and M3 here, and let's draw vector lines relating to where these particles are at. So R1, R2, and R3 are simply, they're not velocities, it's the vector going from the origin to that individual point. And then if we multiply those by their masses, we then have new vectors relating to not only its position, but also its density. And that's going to shrink or grow what we're talking about, the particle we're talking about there. And if we take all 3 of those new vectors relating their mass to their position, and we add them together, we're going to, make a nice big triangle. And we're going to have a resultant vector that is all 3 of those individual particles added, their positions added together. Funny enough, if we then remove the mass from that calculation by dividing it out, we end up with a center of mass calculation that essentially is how all 3 of these particles interact as a system together, but in one location. So this little red arrow here is the center of the mass of these 3 particles acting as one unit. This stuff is valuable to get and understand for a variety of applications, construction, stuff like that. A lot of kinematics related to the body can really care about knowing where center of mass is. So it looks super, super complicated, kind of is. And when we go over examples here, we can discuss what we're doing here. So let's go over 9.16. Hopefully that helps expand the concept a little bit. So using data from the textbook's appendix, I'll give you the data here. Determine how far the center of mass of the Earth-Moon system is from the center of the Earth. And compare this distance to the radius of the Earth and comment on the result. Ignore all the other real things that are impacting the Earth-Moon system. So we can pull the Earth and the Moon's radius from the textbook, and the mass of the Earth is 9.75 times 10 to the 24th kilograms. Mass of the Moon is 7.36 times 10 to the 22nd kilograms. and the distance between the two from the center of the Earth to the center of the moon is 3.82 times 10 to the 8th meters. So what all this stuff kind of boils down to is if we sum everything we're talking about with respect to the masses and the distances, and then divide the masses back out of it again, we end up at a center of mass. There we go. Related to those locations, and we can also, as shown here, do that with velocity for moving objects. So I look at my centers of gravity, my masses, and my distances here. The distance from the Earth to the Earth is 0. The distance from the moon to the from the Earth to the moon, as shown here, and divide out my masses to get a center of gravity at 4.64 times 10 to the 6 meters. So the center of mass of the Earth and the moon is 4.64 times 10 to the 6 meters from the center of the Earth. Well, the radius of the Earth is actually larger than that. So the center of the Earth-Moon connection is some 1,000 miles or so below the Earth. That's kind of crazy, right? The Earth is so much larger than the moon. The moon is so close to Earth that if you were to balance those two together, you'd have to be inside the Earth to hit that balance point. And that's kind of cool. Shown here, this is the one I skipped, but if there's anything, if you're having issues with this concept, go through 9.17 on your own, because that is determining the center of mass of a salt crystal, and there's a lot of stuff in that crystal. And the equation, I'll just scroll down here, gets pretty intense, but we're still following the same basic conversation. And this is a prime example of make sure that you're not writing sloppily, and make sure that you're following your notes and following your knowns, your unknowns, and your equations, right? Make sure, if you got the time and you want to expand on this again, walk through 9.17 on your own. If you can follow that, you're doing pretty good. So yeah, suggest you look at. There you go. Yeah. 9.36. As I said before, you can do any shape really for this. You just need to integrate over the radius of what you're talking about, as shown in this example here. I'm not going to go over this particular example, but we keep going over the same song and dance about all this jazz. One of the last things I want to get into is equation 9.36, this guy here. This is going again back to the conservation that we talked about earlier. Center of mass is in the linear momentum and collisions chapter, because center of mass relates directly to momentum. Conservation momentum is expressed in terms of center of mass of a system. Notice that an object moves through space with no net external force acting on it. As said here, if you stand on a basket and pull the straps of the basket up, you don't go up, right? Because internally, the internal forces in a system have no impact on the external momentum of the system. That's why center of mass is useful for these calculations, and it's kind of always inferred, actually. Always inferred. You're discussing center of mass, because center of mass is, when you adjust center of mass, you're applying an external force and doing things. I want to touch on that and this equation again, and the proof of it shown up earlier, connect these ideas together. The last section is on rocketry and rocket propulsion. It is I'll show you the equation right here. It is a calculus equation dictating forces given a depleting mass of using up your fuel. I skipped over these, I think, in the homework as well. They're not, it's more of a fun application than anything novel to the conversation. But if you want to run through some of these examples, like 9.20, feel free to be my guest. There's some good calculus work in here. That is chapter 9, linear momentum and collisions. Hope you got something useful out of this. There is a lot of seemingly difficult material here that if you just take your time, write it down slow and take a breath and grab a glass of water if you get confused, you'll be able to get through just fine. So that all being said, thanks for spending time with me and take care.